Okay, so one of the important derivatization of monosaccharides is, of course, the formation of a disaccharide. Basically, you're derivatizing your monosaccharide with another sugar. Okay, and so basically, the formation of monosaccharide happens by the linking of another monosaccharide, and it happens also through the through a bond to the anomeric carbon. Okay, and because this bond involves the anomeric carbon, the bond that's formed is also a glycosidic bond. And so, three of the most common disaccharides found in nature are sucrose, maltose, and lactose. So let's take a look at lactose. So lactose is a major carbohydrate in milk. Okay. Yeah. By the way, so the reaction also happens um, through the reaction between one of the hydroxyl groups of the other sugar, reacting with or forming a bond with the anomeric carbon. Okay. So for lactose, well, it's a sugar that's found primarily in milk, okay, and it's the major carbohydrate in milk, and it's produced only in lactating mammary glands. Okay. And this, as it, this lactose as a disaccharide needs to be broken down into its component sugars before it can be absorbed into the bloodstream. So this is the systematic name for lactose, and we'll see how we go about this systematic naming. So lactose is characterized by two D sugars. So it's D-galactose and D-glucopyranose. So you have this D-galactopyranosyl, D-glucopyranose. And that's how you name those two. They're joined by an O glycosidic bond. Okay. Again, because of the alcohol group in glucose, okay, formed the oxygen in the alcohol group formed a glycosidic bond with the anomeric carbon in the galactose. And since it's a hydroxyl group, an oxygen is involved, and so it's an O glycosidic bond. And the linking is between C1 of galactose and C4 of glucose. So that's why you have this parenthesis 1 arrow 4 that refers to the linkage. Okay. This galactopyranosyl has a beta attached to it as a prefix because it's the beta hydroxyl group that was lost during condensation. So this is essentially basically the beta anomer of galactose that reacted with glucose. So it's not the alpha anomer of galactose that reacted, but the beta anomer. That's why you have this beta designation. It's the beta hydroxyl group that was lost it's the beta hydroxyl group of the anomeric carbon that got lost during the formation of the glycosidic bond. Here, the structure that's shown here is the beta anomer. See, the hydroxyl group of the anomeric carbon is on the same side as this terminal primary alcohol group. Okay, and so this is the beta anomer, and so that's why we designated this as the beta anomer. Okay. If it so happened that I presented the structure here where this hydroxyl group of the anomeric carbon is pointing downwards, then I'll say that this is the alpha D glucopyranose. But as is for lactose, this can actually interconvert between the beta D glucopyranose form and the alpha D glucopyranose form because, again, of beta-rotation. So the alpha anomer can exist in equilibrium with the beta anomer in aqueous solution. Now take note that the linkages here, okay, is important. If it so happened that the alpha anomer of galactose is the one that form the glycosidic bond with glucose, meaning this is going to be an alpha D galactopyranosyl. So even though, okay, the linkages are going to be the same, it's still going to be C1, C4, but if this were alpha, that would be a different disaccharide. That will not be lactose anymore. So lactose in particular is this structure here. So is lactose a reducing sugar? Yes, because you have in a way technically a free anomeric carbon here. Because of mutual rotation, you can break this bond to produce your aldehyde. So maltose. So maltose is a component of malt, and um, so malt drinks that has maltose in it. It's also very important in the brewing of beer. And this is its systematic name. And let's see why it was named this way. So it's a homodisaccharide, meaning the the same sugars bound together are bound together by glycosidic bond. So you have a D-glucopyranose bound another a D sugar glucose bound another D glucose. Okay. And in particular, the anomeric carbon that was the source of the anomeric hydroxyl group during condensation is the alpha anomer, and that's why it's alpha here. And in particular, this linkage is what's known as an alpha 1,4 linkage. Okay, because the anomeric carbon, okay, that reacted with another monosaccharide to produce the disaccharide, it's the alpha anomer. So it's the alpha hydroxyl group that was lost during condensation. And so we say that an alpha 1,4 glycosidic linkage was formed between the two monosaccharides. Okay. And of course, the way the structure is presented here, the alpha anomer of glucose is the one that's pictured in this structure. So that's why we name the structure alpha D glucopyranose. Again, due to mutation, the beta anomer of this glucopyranose can also exist in equilibrium. Is this a reducing sugar? Yes, because through mutual rotation, this bond can be broken and you're going to have an aldehyde that can act as a reducing agent. Okay. Now, how about fructose? So this is the most, basically the most abundant disaccharide, and we know this more commonly as table sugar. So it's characterized by two monosaccharide residues. You have D-glucose and D-fructose. And in particular, it's the alpha anomer um, of glucose that supplied the hydroxyl group. Okay. So the two residues are wanted to link in particular, or you can say alpha 1 to linkage is the glycosidic bond. Now, I want you to take a look at the structure here. Compare it to, let's say, maltose. For the second monosaccharide, okay, was it the monomeric, was it the anomeric hydroxyl group of the second monosaccharide that reacted with the first monosaccharide? So it's not. Your anomeric carbon is still here. There's your anomeric hydroxyl group. If you take a look at sucrose, where's the anomeric hydroxyl carbon? It's not this one because it's not attached to another hydroxyl group, but it's this one. Originally, this is the OH group, so this carbon is attached to two oxygens, the hydroxyl group and the oxygen in the ring. So this is your anomeric carbon. So now there's a difference between these two structures in that sucrose. Okay, for sucrose, the anomeric um, carbon, okay, of the other monosaccharide also participated in forming the glycosidic bond, and that's why it's named as a furanoside. Okay, it's not a furanose because well, basically this is a glycoside because um, a sugar, as I mentioned, a sugar that um, bonded through its anomeric carbon is already a glycoside. Okay? So they're one to two linked. Okay. So as I mentioned, the glycosidic bond is now between the anomeric carbons of both residues. Okay. So because of this one, your anomeric carbon is essentially now not free because it's already bonded. Both anomeric carbons are bound to each other through a glycosidic bond. Mutation will not be possible because this is not a free anomeric carbon anymore. And so this cannot equilibrate between alpha and beta anomers. So in the same, using the same reasoning, would sucrose be a reducing sugar? No, because since mutation is not possible anymore because your anomeric carbons are not free, mutation is not possible. And then, so that means your sucrose cannot act as a reducing sugar. Okay. Yeah, so we've gone through sucrose, we've gone to maltose, so cellobiose. Okay, how will we name this? I mean, naming this is straightforward. You have a glucose, you have a glucose. So I guess first thing you can take a look at is the anomeric carbon of the next monosaccharide still free after the reaction? It still is. This is the anomeric carbon. So you're going to name this as a glucopyranose instead of a glucopyranoside. Okay. So you have, is it a D-glucose? Yes. Your CH2OH is on top. Yes. Your CH2OH is on top. So both of these are D-glucose sugars. Where's the linkage? It's between C1 of the first monosaccharide and C4 of the next monosaccharide. So how is the linkage? So sometimes you'll see these curved bonds here. Okay, sometimes you'll see this. So this designates that this reacted with the hydroxyl group that's on top. Okay, on the same side as this alcohol group here reacted with the hydroxyl group that's on the same side as the CH2OH group. So this anomeric hydroxyl group is on the same side as the CH2OH group. So this is the beta anomer. So you're going to have a beta D glucose. Okay, so yes, so you have two glucose, so D, both of them are D, both of them are the beta anomers, okay, and the linkage is between C1 and C4 of the next monosaccharide. So you can describe this as having a beta 1,4 linkage. Okay, so you've actually seen another sugar previously where it's an alpha. It's a 1,4 linkage, but it's an alpha. Um, Linkage, and that's maltose. See, essentially for maltose and cellobiose, it's the same. Everything's the same except for the fact that it's the beta anomer of glucose that reacted here in cellobiose. For maltose, it's the alpha anomer. Okay. And that makes them different disaccharides. So you can consider them to be, in a way, I guess, like isomers. Okay, where they only differ in this in the configuration around this carbon. So they can be epimers. So beta maltose here. Wait, let me see.